Yeah. Okay. So, hi everyone. Good evening. Welcome to the final session. This is an extra session for the computational complexity course on NPTEL. And my name is Bhavya. Okay. And so, in this session, what is the objective of this session? Uh, of course, this is a sort of recap on what we did so far. Okay. And not only that, um, we could quickly sort of discuss if you have some kind of doubts. Okay, in any of the content, or maybe if it is even remotely related to complexity theory. And finally, I also want to talk about the frontiers of complexity theory right now. Okay, and what the current state of art research is happening in complexity theory. Okay, so yeah, let's go on. So I just want to do a quick recap. Okay, so let's start from the beginning, or if you have any other suggestions, you can let me know. But I think I can start with a quick recap, right? Or what do you think?
Yes.
Yeah. Okay. Okay. Great, Suraj. Okay. So that's fine, right? Well.
Yes, yeah.
Yeah. Okay. Okay. Sure. So complexity theory. Okay. So what is complexity theory? Uh, it is the study of computational hardness. Okay. What makes a problem difficult, and how we can categorize problems into, you know, difficult or less difficult. And how do we do that? Well, we have several techniques. Okay. And one technique is the main technique is using reductions. Okay. What is a reduction? Okay, a reduction is a way to transform a problem A to a problem B. Okay, transform a problem A to a problem B. And what is the general idea? How do we show hardness? Okay, we show that a problem A reduces to B. Okay, so A is, if A reduces to B, any problem of A can be converted to a problem of B. So, and this is how we show, to show A is hard. Okay, show that show A reduces to B where B is a known hard problem. So sorry, the other way around. To show B is hard, okay, show that A reduces to B where A is a known hard problem. Okay, and
So,
yeah,
so, yeah. So this problem B would be at least as hard as the problem A is.
exactly. So this, we have
And
this greater than equal to sign, right, or less than equal to sign, and it is sort of like comparing hardness, right? So it's sort of like A is at most as hard as B, or B is at least as hard as A. So
so
this,
then,
right?
yeah, but then nothing can be said about the hardness of the problem B except that the problem B is at least as hard as the problem A is.
Exactly. Because if, yeah, right. Because if A were easily solvable, okay. Sorry, if B were easily solvable, then A would be easily solvable.
Right.
Right,
Yes.
right. So that is the general notion of hardness, and we've seen this in computability theory also. But we are talking about complexity theory now. The notions of hardness will still work here. Okay. So now what we have is that, okay. So what do we define as easy, and what is hard? Okay. So what is this? So now we have a notion of computational resources. Okay. So we have computational resources, and the most popular ones are time and space. Okay, space meaning the memory taken by the program. But complexity theory does not only treat time as space as and space as supreme. We have something like non-determinism, which is also a resource. We have randomness, which is also a resource. Okay, and you can take I mean several examples, and So you can look into it, and there is something called Bloom's axioms. Okay, it's by Manuel Bloom. Okay, and most of the computational resources follow Bloom's axioms. Okay, you have it should follow some kind of transitivity relation. Okay, and it should have some kind of subadditivity. So that is the ideas, and you can look into it. Okay, Bloom's axiom. So he gives some kind of suggestions on what would make a good complexity resource. Okay, now you have complexity resources: time, space, non-determinism, randomness. Okay, and then you can add more things to it. Okay, and so what qualifies as easy and what qualifies as hard? Okay, so in general, when we talk about this, okay, we in terms of time we call polynomial time to be easy, and hard is anything above polynomial. Okay, and super polynomial, anything above polynomial is hard. And in terms of space, we have logarithmic spaces, something that is desired. And what is hard? Well, anything above logarithmic, that is something like super log. Now this may vary. Okay, sometimes maybe even say quasi polynomial time is fine with us, but exponential time is hard for us, or super exponential time must be hard for us, and so on. But this is a general accepted notion. Okay, so it's something to work with. Okay, we can modify it as we go, and so now and it's we can do it in terms of randomness also. We can do it in terms of non-determinism also. Okay, and I'll come to that point. Okay, what is easy and hard in terms of randomness and non-determinism? But now comes the problem of, okay, fine. So you have easy problems and you have hard problems. Okay, you have easy problems and you have hard problems. And there is a set of easy problems and there is a set of hard problems. And then you have, let's say, harder problem. And you have a problem which is harder than this. Okay. Can you even say that, okay, such kind of things exist? Can you even say that, okay, you have an easy problem, then you have maybe there's a problem which is easier than it, an easier problem. Okay, can you categorize them in terms of, let's say, time or space and so on? Or can you say that, okay, this means this does not exist? Let's say this doesn't exist. Let's say all problems are equally hard or all problems are easy. So this was the kind of fundamental questions that complexity theory people were asking. Okay, and so one of the first theorems that people discovered, okay, which led to the foundations of complexity theory, was the time hierarchy theorem. Okay, so that is, you actually have a strict hierarchy. What does the time hierarchy theorem say? It says that time of f of n is strictly contained in d time little o of f of n times log n, or f of n, that it would be more correct to say uh, f of n little o of log n. Okay, so this is what the time hierarchy theorem said. What does it mean? It means if you give me strictly log n more time, I can decide strictly more languages than what I could previously do. For example, this is, let's say, d time, okay, n, okay. Then there is always a problem here which cannot be solved given linear time, but can be solved if given n log n time. And if this is d time, this is in d time n log n, right? Then there is strictly a problem. Okay, there is strictly a problem that cannot be solved given n log n space, but it can be solved if you give me just d time n log n times log n, which is n log square n. Space, time. Sorry, not space. So, and this goes on. This goes on. So the hierarchy theorems is one of the first, and you can achieve the same for space also. and which has the same flavor, that if you give me more space, then a little bit more space, then I can strictly decide more problems. Okay. And you have time hierarchy and space hierarchy. And what if you bring non-determinism into the context? So now it is true for non-deterministic also. There is a non-deterministic variant also which says the same thing. Make both sides n time, and you are done. Okay. So this is what time hierarchy and yeah.
So what is there in the space hierarchy?
Okay. So space hierarchy is also the same thing. Okay. So it says D space f of n is strictly contained in D space f of n times little of log n.
Okay.
Okay. It says the same thing. Okay. So,
Okay.
so and this has inspired a lot of theorems called what are known as hierarchy theorems. Okay. You bring in a complexity resource or a complexity measure and a complexity resource, and then for that, can you establish a hierarchy? Because can you, as soon as you say, okay, I introduce a complexity. Okay, as soon as I say I introduce a complexity measure, you include a new measure. Let's say the number of times a Turing machine moves left or right. Okay, can you add a hierarchy theorem to it? And if you see the polynomial hierarchy, it is also a hierarchy theorem, right? It is a hierarchy theorem on the oracles, or you can even see it as alternations, right? So that is what led to hierarchy theorems. Now we say, okay, fine. So it's I okay, but it is difficult to work with these small space classes with just little bit difference, right? Log n difference of computational resource. So I say, okay, I don't want to work with that level of detail. Okay. And what I do is I'll club them together. I'll say, okay, I'll say I put n to the c time, n to the 100, n to the 101, and n to the 1000, everything time in the same basket. I call them the polynomial resolvable languages. Okay. And which is nothing but P for us, deterministic polynomial time. So you have P. What is P? P is nothing but union of all the languages, okay, which take deterministic polynomial time, n to the c, and n is at least 0. Okay, and this is the class P. And similarly, what is NP? Okay, of course you can define it in the non-deterministic way. That is, n is at least 0, n time of n to the c. Polynomial time, but uses non-deterministic Turing machines. Now we come to the question of P versus NP. Okay. Now before that, what is NP? We say non-deterministic polynomial time, meaning that my non-deterministic Turing machine makes several guesses on the way. Okay, makes guesses on the way, and even if there is one correct guess, okay, even if there is one correct guess where it accepts, then the Turing machine is set to accept. That is what a non-deterministic Turing machine is set to be, even if others will reject. Even if others will reject. So that does not matter to us as long as one. Okay, thank you. So as long as one of them accept, even one of these paths accept, we are fine with it. Now, and so it takes polynomial time across all computational branches. So this the depth of this tree will be polynomial. Okay, but let's say I want to do a deterministic simulation of it. Then we've already seen that I need to explore all possible guesses, all possible paths here. So definitely we have that it takes exponential time because the number of different paths is exponential in size. So we have that any non-deterministic polynomial algorithm, okay, non-deterministic polynomial time algorithm can be deterministically simulated in exponential time. That is good. Okay, fine. Now next, what do you have? Next you have that the depth is polynomial, right? Now what we think of is, okay, fine. What if I have a model, okay, where actually I tell you the correct path if it exists. If there is an accepting path, I will tell you the path. Then what can my machine do? What I'll do is I'll just verify if what you gave me is correct or not. I'll just only travel that path which you gave me. If and I'm a very honest person, and you are a very honest person, you always give me the correct path if it exists. By correct path, I mean an accepting path. If it exists, then fine. I check it. If you are, and you are always honest, okay, if it exists, then I will definitely reach accept. This is another way to view non-determinism, that is in terms of certificates. Okay, that is, this accepting path can be thought of as certificates. Getting it? This accepting path can be thought of as a certificate. And so now there is a definition. Certificate definition is that NP means there exists a verifier which is efficient, which means polynomial time. Okay, polynomial time verifier, such that if X belongs to the language, okay, L, then there will definitely exist a certificate such that my verifier machine will actually say yes. So this is the verifier definition. Now I can have several NP problems. For example, a satisfiability. Okay, check if a formula is satisfiable or not. Satisfiability, checking if a formula is satisfiable or not. And similarly, you have graph isomorphism. Given two graphs, G1, G2, G1 is isomorphic to G2. Prime or anything, okay? And but what is the certificate here? Here the certificate is the satisfying assignment. This is the certificate way of seeing it. The non-deterministic approach would be, I guess every possible assignment. Even if one assignment satisfies, my machine will accept. Okay. Graph isomorphism, I go across all possible permutations that assign different labelings. Even if one labeling is correct, then I'll accept. That particular labeling which is correct is my certificate. So now what I can say is that NP problems are easy to verify given certificate. Sometimes it's just called easy to verify, but it does not easily make sense. Okay, and P problems are easy to solve, and because they are easy to solve, they are actually easy to verify also. Verification seems to be, philosophically, verification seems to be more harder than solving. Okay, that is where we come to the idea of P versus is okay. Is solving more harder than, that is what we are asking. Sorry, I think I flipped it. Okay, solving seems to be strictly more harder than just verifying. Okay, so the question is this true that P equals NP, or P is not equal to NP? So this is the bedrock of what computational complexity is built upon. Okay, and now that I have introduced P and P, okay, now I won't go into NP completeness, but we all know the definition of NP completeness. That is that every language in NP will reduce to NP complete language, and this was sort of the very early attack on P versus NP problem. That is, we try to come up with an algorithm to solve an NP problem. Okay, to solve to NP complete problem, and if we can solve it in polynomial time, then we show that P equals NP. Of course, but that is very unlikely to happen. Okay, but now we have this entire web of complexity classes. Okay, that we can similarly define in the same grounds. We have P, and we know that P is contained in NP. Now, what we can think of is, we can think of co-NP. Okay, we can think of co-NP, and co-NP is all the languages which are complement of those in NP. Okay, and P is equal to P complement, co-P. Okay. Take any language in P, complement it, it is in P. Why is that so? Because I think we saw that we just flip the accept and reject, right? And so we have this. Another thing I want to again mention is, let's say you have P, let's say you have NP, okay, and someone proves, let's say, that P is not equal to NP. Okay, P equals NP, I don't care, okay, but P is not equal to NP. Let's say P is not equal. Then you have NP complete problems, and you have P problems. And of course, if P is not equal to NP, then obviously I cannot have an NP complete problem here, because if that would happen, then P is equal to NP. Question is it so that this entire place would be filled with NP complete problems, or will there always be a problem which is not NP complete? That is, let's say this is NP, then this is NP complete. Is this possible? And that is what Ladner's theorem is about. He says that if P is not equal to NP, then there exists a language L such that L is not NP complete. And such languages are what are called NP intermediate problems. And graph isomorphism is a good example. Okay, graph isomorphism is believed to be an NP intermediate problem. Firstly, we already believe that P is not equal to NP. There are numerous evidence for this to happen. Okay, and secondly, since that happens, then due to Ladner's theorem, we are guaranteed to have some problems which are not NP complete, but they are not NP. Now, Ladner's theorem says that, okay, by Ladner's theorem. Now, graph isomorphism is a problem which is there. And yeah.
So is this a special problem like say graph isomorphism or NP intermediate problem is the one which is there in co-NP as well?
Okay. So you mean, let's say NP is not equal to co-NP.
Yes, but then there are problems at the intersection of the NP and the co-NP. So I'm having this impression that as if the problems which have been attempted, are most of the problems which are there at the intersection of these two classes. Like say the problems which are like say the problems that like say testing whether the given number is a prime number or not, or say the graph isomorphism problems. So most of the problems which have been attempted, I think, belongs to the NP intermediate class. So
Testing whether it's prime or not. The
yes,
primality
given
is
number
already in P.
primality is in P. Yes,
Yes.
checking. Yeah, but yes, it is in P. Checking whether a given number is a prime number or not is in P, AKS algorithm. But yeah, but so I mean, does this mean that the problems which are NP intermediate are there at the intersection of NP and co-NP?
Okay, that is interesting. Well, is it at the intersection of NP? That I'm not sure. That is interesting. Well, I mean, NP intermediate problems, they have their own flavor, but I'm not. What we would want to see is that why do such problems even exist? Why do NP intermediate problems even exist? There should be. It has a certain sense of hardness and a certain sense of easiness to it. And
Yes, yes.
if P is not equal to NP, okay, so here's the question: if P is not equal to NP, does that mean that NP is not equal to co-NP?
So yeah, so if P is not equals to NP, so then maybe, but I exactly don't remember. But then probably this works in the forward direction and may not work in the backward direction, kind of the thing. So I don't remember actually.
Yeah, I don't think so. I mean, yeah, I don't believe so. P is not equal to NP does not guarantee anything about NP not being equal to co-NP. But
Yes,
all we can
maybe,
guarantee
maybe.
is that if P is equal to NP, then NP is equal to co-NP.
Yes, that we know. That we know.
Yeah.
And its
So
reverse may
yeah,
not
yeah,
be true. Yeah.
yeah. So to directly say that the sort of graph isomorphism or NP intermediate problems lie here, if NP is not equal to P, that may not be true. That is what I believe, but it would still be an interesting statement. Why? Because now what you are doing is that would mean that if P is not equal to NP, this entire area which does not intersect with co-NP are all NP complete. So what you mean is right.
Yes, yes.
Yeah, that would be. Oh, okay, but P is not sitting there. Sorry. P is sitting here, right? So this is P, and this is NP complete, and this is NP intermediate. Um, yeah, not sure why it would force, but definitely the fact that uh, it could be a possibility. Yeah, it could be a possibility. I can understand why this. The intuition may be that these languages are slightly easier because they are closed under complementation.
Yes,
Yeah,
yes.
but
Right.
I'm not sure about this fact. Yeah.
Yes, yes,
Okay.
yes.
So okay, great. Okay, so now you have P versus NP problem, and then you have NP versus co-NP problem also, and then you have uh, you know that this can be simulated in exponential time. Okay, but now we talk about space also. Okay, we have that NL can be simulated in P time. Any NL can be simulated in P time, and any any L is contained in NL, non-deterministic log space. And now here you have an interesting thing about space. Okay, space is closed under complementation. You don't know if
Yes,
n yeah,
Immersman, yeah.
yeah, right, Immermann-Zalapsini, and space is closed under complementation. And similarly, NP and co-NP, by the same argument that NL is contained in NP and co-NP can be simulated in polynomial space. And by the same argument that NL is and by Immermann-Zalapsini, you have that this is equal to NP space. Sorry, not Zimmermann-Zalapsini. By simple observations, you can say that okay, non-determinism does not matter if given more than polynomial space. And by Immermann-Zalapsini, you have co-P space. It is closed under complementation, and non-determinism. Okay, there is no P space versus NP space here. Okay, it's already closed for us, but there is NL versus N. So this is another open problem. And finally, P space itself, okay, is trivially contained in EXP. No, not trivially, but the argument is similar to why NL and L are contained in P. Okay, EXP, and EXP itself is contained in NEXP. And why do we say NP versus P? Why do we say P versus NP, not EXP versus NEXP? Because well, there are theorems which use a technique called padding, which says that if P is not equal to NP, then NEXP is not equal to EXP. We can use the same proof to actually handle NEXP and EXP. Okay, so we don't know of conditions where these P and P cannot be translated to larger classes like NEXP, EXP. For example, even if you work with NL, L, and so on, then it will translate to P space similarly. Okay, and as you go higher up, okay, the hierarchy, the resources you are allowed to use is even more and more. So it gets easier to translate the more restricted case to the bigger case rather than the opposite direction. Okay, and you have this L, NL, and so on. Okay, and this is what are your classical complexity classes. And now what you have is let's talk about randomization. Randomization is that now it is a slightly more powerful form of non-determinism. Okay, where uh, you are allowed to toss some random bits. Okay, and then and then your algorithm is able to make some random choices. And so you can say that if a lot of random choices for a lot of random choices, if your answer is yes, then you'll accept. If not, then you'll reject. So that is how your simple randomized algorithm works. Okay, the probability over random variables that your algorithm on the input accepts. If it is greater than 2/3, then your algorithm is supposed to accept. And probability that on is rejects, okay, is 1, is at most 2/3, and this is when x is in L, x is not in L. And this is what is called BPP. And BPP trivially contains P. Question is, does BPP contain NP, or is BPP contained in NP? Well, it is believed that BPP does not contain NP. Okay, BPP, people say that BPP is close to P. That is, randomness can be completely removed at no expense, almost no expense of time. Okay, and this is what is called de-randomization. I'll talk about it later. That is, remove randomness. And it may seem very, you may say, why would I come up with such kind of algorithms? Well, there is something called error amplification by using Chernoff bounds. You saw in the lectures that you can reduce this error probability by a very small fraction, some 1 by 2 to the 1 by exponential fraction, which is so small that practically if you implement those algorithms, the chances of errors are so small. Okay, are just negligibly small. Okay, so a lot of practical algorithms, for example, like what Google uses, the search and ranking algorithms, are all randomized algorithms because you are working in very large graphs of billions of nodes. Okay, so you cannot afford to use deterministic algorithms. You need to use randomized algorithms, right? So you have this, you have BPP, and now you have other classes like ZPP, and you have other classes like RP, co-RP. These are all one-sided error classes, and ZPP is contained in RP intersection co-RP. In fact, it is exactly equal, and this contains P. ZPP contains P. Now, there is another question whether you can de-randomize this also. Okay, but we do not know a way to de-randomize ZPP. Just to remind you, ZPP means on average over the random bits, your this does not make any errors. Okay, it gives the correct answer. Okay. And finally, we talk about circuits. Okay, and what are circuits? Well, circuit is another computational model. Okay, where you have AND OR gates. Okay, and formulas are just circuits where you don't have fan in fan in more than one. That is what is, sorry, not fan in, fan out. That is the number of outputs to each gate. This is feeding to two gates. The output are feeding to two gates. This is not allowed in formulas. It is a circuit, but not a formula. Okay. So a formula, in other words, is a tree or a DAG, not a DAG. It is a tree. A circuit is a DAG. Circuit is a DAG. A formula is a tree. Now, why are circuits and formulas interesting? Well, one reason is that the class P, okay, has polynomial size circuits. Okay, has polynomial size circuit. In fact, what you call P uniform P, those circuits whose description can be computed in polynomial time, is exactly equal to no, I won't write that. P uniform, P uniform P slash poly, which means the circuits which can be polynomial size which can be computed in polynomial time, okay, is exactly equal to P. So it is, you can almost say that poly size circuit is equal to P. You can almost say that. Okay. So what you want to do is, if you show an NP complete, and not even NP complete problem. Yeah, NP complete problem. No, yeah, not even NP complete. If you show an NP problem that requires at least super polynomial size, then what do? You say, okay, here is an NP complete problem. Not an NP complete problem. Here is an NP problem which requires at least exponential size circuits, or even, let's say, n to the log n size circuits. Anything greater than polynomial, it requires at least super polynomial size circuits. But P requires polynomial size circuit. P is happy with polynomial size circuit. So how can it be that P is equal to NP? It cannot be. So this is a way to separate P is not equal to NP. And this is what are called lower bounds. That is a problem. The size of circuit required for a problem is at least something. This is what is called a lower bound. Okay, and lower bound help separate complexity classes. Okay, so and so you so this is the application of circuit. Surprisingly, there is a bridge, okay, to the circuit world and the classical world, that is P slash poly. BPP is contained in P slash poly. Okay, and P slash poly is a very strong class. Okay, another way to interpret it is you're given advice here. I won't go deep into it. I've already done it before. Okay, but yeah, now you can define other types of circuit classes. You have NC1, NC2, and so on. You can show that I did it in one of the problem solving sessions, how NC2 contains NL. What is NC2? NC is log depth, okay, poly log depth, and bounded Fanon poly size. And AC is again poly log depth, unbounded Fanon, and again poly size. Okay, and you have this NC 0 is contained in AC 0 is contained in NC 1 is contained in AC 1 is contained in, and so on. Keeps going like that. And you have other circuit classes, okay, which like TC and so on, which are not relevant for this talk. And NC1 actually contains L. In fact, uniform NC1 is equal to L. So you can actually, it's more correct to say L contains NC1. Okay. And it goes on that way. So BPP is contained in P slash poly. And okay, this is about circuits. Okay, and an important, okay, but I won't mention that in the interest of time. And finally, you have communication complexity. Okay, communication complexity. And communication complexity is a very interesting area where you actually obtain lower bounds using what are called communication games. You have Alice Bob, and they exchange bits with each other, and they are trying to compute a function xy such that Alice is given x, Bob is given y. Well, one trivial way is that Alice sends all her bits to Bob. Alice sends the entire x to Bob. Bob computes f of xy, and then he sends one bit saying what is f of xy equal to. And so it trivially requires linear number of bits, trivially n plus 1 number of bits. But can you minimize this? That is the question. Okay, it is of independent interest also, but there is a huge result which is called the Karchmer-Wigderson theorem. And Karchmer-Wigderson theorem says that, oh, you know, if you have a circuit or if you have a formula phi, and it computes some f. Okay, it computes a function f. Okay, not computes f. Okay, I have a function formula phi, and I have the following game where Alice and Bob are given x and y, and they are supposed to exchange bits, okay, such that and phi of x is equal to 0 and phi of y is equal to 1. Okay, and so they don't match, and since they don't match, they have at least one position where they differ, x and y differ. So they need to come up with an index I such that x at position I is not equal to y at position I. This is the game that they play, and this is what is called a KW game. Okay, and the deterministic communication complexity, there's a number of bits that I need to exchange, is of the Karchmer-Wigderson game, this particular game where I need to figure out the index, okay, for that phi is actually equal to the depth of the circuit. depth of the circuit phi. And you have now a bridge between communication complexity and circuit complexity. So you can prove circuit lower bounds using Kashmir design. Once this result came about, this was about, I think, 90s. Okay. Once this result came out, there were lots of lower bounds proved. Okay, left and right. And there is a related theorem which I will talk about later. Okay, but that is about circuit communication complexity. There are, I mean, several interesting techniques in communication complexity which I discussed in the problem solving sessions, but right now, due to interest of time, I will not be discussing it. Okay, so and interactive proofs. Should I really do a recap? I don't know, but I'll let you guys decide that. And so just let me know if you have any questions, further questions, and I'll move on to the next part. Okay.
Yes, so that would be, I mean, this is such a nice summary of the entire thing which we did in the 12 weeks. Almost everything is covered. So, yes. So my query is that can you, can you tell the roadmap, or can you guide that how to start doing some research in this area, computational complexity? Because I tried to read one general, say, theory of computing, and which is probably considered to be a very standard journal in this area, and
Right.
even I could not understand the title of the papers. So,
Sure.
I
Yeah.
mean,
So what I recommend you do, okay, is don't start reading journal papers directly, okay, and especially because journal papers are very much in depth. Conference papers are shorter, okay. So here's what I recommend you to do: don't don't start reading papers right away. Although, I mean, if you can, then good enough for you. But if not, then actually what you see is, conference recordings. Nowadays what you have is that these conference, okay, see, unlike uh, uh, pure sciences fields like physics and physics, chemistry and stuff, medicine and stuff, where you try to publish in very good journals like Nature, Science, and so on. um, Mathematics, okay, and theoretical computer science, and even some fields of computer science like systems, we are more interested in submitting in very reputed conferences instead of journals, okay. And the good thing about conferences is that a person comes and gives a talk on their paper, okay. And a good thing about conference recordings nowadays is that um, they are recorded and uploaded to YouTube, okay. So there are some very reputed conferences, okay. One is Talk, okay, very reputed, and another is Fox, and another is Stacks, and another is ITCS, okay. And these are very reputed conferences, okay. And speakers, and there are many more, okay. But there are some which are more um, focused on algorithms also, okay. So but these are more specifically on complexity theory. For example, stock is very much a complexity theory based place, okay. And you go there, okay, and see the list of papers, and go through that, and check if there is something interesting there. You can read the abstract, read the title, and so on, and then let just go to YouTube and then watch the talk there, and you'll gain a lot. You'll learn about the different problems, and they'll start with a simple introduction, okay. And the material also they'll cut it down, because they need to present it only in 1 hour less. So they'll cut down the material and make it into bite-sized chunks so that you can easily digest it. So uh, that's what I recommend you do. You check out the list of papers, shortlist some interesting papers, okay. And the people who are publishing in these conferences are all working in the frontiers of complexity theory, so you don't need to worry if there is any outdated content or not, okay. And check out the list of papers, and then you check out the abstract, and then go to YouTube and then look for Stock, Fox recording, whatever, and then you'll have the presenter who will present it. and that will be a much more simpler task, okay, than directly jumping into it. Then what you do once you get that, and then you get a slight introduction on that topic. Now you have a topic, okay, and on the field that they are working on, let's say communication complexity. Now what you can do is, uh, you can look for their paper and then start reading it, okay. And it's okay if you don't understand it. I mean, Rome was not built in a day. So it is something that takes a lot of patience and a lot of effort, but eventually with enough time, right? So with enough time, you will get it definitely, okay. So and once you do that, then you can follow the work. So, and another thing is, um, subscribe to ECC, ECCC, okay, European Computational Complexity Conference. So this is a free um, publishing platform for complexity theory. So people publish in ECCC for free, okay, and they publish for free out here. And this is also to show that, okay, I've done the work, and so that people don't point fingers at you, okay. And let's say because journal conference accepting times are very overlapping, and if two people's work overlaps, then there's no way to tell who came up with it earlier, okay. So a lot of people publish it here directly in ECCC, and later they publish in conferences also, of course. And of course, archive, and the complexity part of archive, not the entire archive, because there are other disciplines here also, okay. And there is also something called computational complexity blog, and this blog is maintained by Lance Fortnow, who is also a reputed complexity theorist, okay. And there are really interesting things here. So regarding how to proceed from here, if you want to do research, okay, in complexity theory, then this is a nice way to start, okay. And then what, once you get seasoned and know about the area a lot, and once you understand a paper, okay, and there is also a question about how to read a paper. There's also a nice, I forgot who wrote it. Was it Richard Karp? I don't know. There is a nice paper which is called "How to Read a Paper in Theoretical Computer Science." Okay, but how do you read a paper? That is another question. You cannot jump into the paper directly. Okay, that is another art which is to be learned, which comes with practice. But just a gist of it, you read the abstract. You read the main theorem first. You don't go into the proofs. You don't read linearly ever. You read the abstract, you read the main theorems, and quickly glance through the proof and see what lemmas were used to prove it. And then you look at the lemmas, and you go a bottom up approach. And then once you finish that, then what you do it, you read from top to bottom. Now you read properly from top to bottom, and then you make several passes until you get the entire paper. That is how you read a paper generally in theoretical computer science. Okay, and but yeah, regarding your question, I think this would be enough, more than enough. Okay, okay, okay. Any more questions before I move on to the? Okay, maybe I'll push the time slightly. Okay, because I have some content to cover. Yeah.
So, any other resource which you would like to suggest, say apart from the courses available on the NPTEL in the area of the theoretical computer science?
Any other resource? Now, see, you've had a taste of the breadth of computer science. Okay. Now, what I would recommend is um, uh, you can go deeper into each of these fields. For example, you can have a course on each of these content which I covered here, okay, which are written here. You can have a course on entire course on circuit. There is a nice course by Raghunath Tiwari from IIT Kanpur on NPTEL called on circuit complexity. You can learn circuit complexity on in depth, and you can have an entire course on communication complexity. You can find it online. Okay, you can have an entire course on de-randomization, pseudo randomness, and so on. And you can have a course on coding theory. You can have a course on So many fields here. You can have a course on, we haven't covered something like computational group theory here. You can have an entire course on algebraic methods for doing complexity theory, and even interactive proofs, right? The final content. You can have an entire course on what is called the PCP theorem. There's a theorem in interactive proofs which is called PCP theorem, which requires an entire course to cover it. Used to require, okay, until a complexity theorist called Irit Dinur, who is very celebrated right now from Israel. She solved the PCP theorem using a very short proof, which is the short proof is around 3-4 pages long, maybe. So the content that required an entire course is now cut down to 2 or 3 weeks now. So yeah, so and there are so many things to learn here. The rabbit hole only goes deeper from here. So that is what I recommend actually. So see, you need not take another course on complexity theory. Okay, so you've already done one course on complexity theory. Why would you do it once again, right? Maybe you can go to the textbooks and revisit it once again, but you don't need that. What I recommend is you look for specific courses now. If you found communication complexity interesting, then look for courses on communication complexity. If you found circuits interesting, you look for courses on circuits, and you pick these out. And believe me, there will be several resources all over the world. Okay, and you can read it, go through it, and so on. And that is what I recommend. That is what I recommend after this. Okay, if you want to learn much more from here. Okay. And yeah, okay. So, any more questions?
So people often ask that what is the relevance of this course computational complexity instead of, I mean, spending time here, I mean, in this subject, better you could have learned something else which has got so many practical applications.
Oh, but how can you say that computational complexity has not got practical application? Well, a student had once asked me, um, he also works in complexity theory area. So he asked me, okay, so people ask me what I do, and we work with algorithms only, right? I said, yeah, we work with algorithms also, and but what we generally do is we prove hardness results and so on, right? We separate classes. But he said, yeah, that is a bit difficult to explain to people. So what is the point of what we are doing? That was what he was asking. And so isn't it easier to say that we design algorithms? I said that, yeah, that is fine. But see, you are actually underselling us by saying that we just design algorithms as complexity theorists. I told him that, okay, you have a problem and you want to solve it. Okay, you want to solve that problem. You have a computational problem. You want to solve it. So what you do is you go to an algorithmist to solve it. Someone who designs algorithms. Well, I mean, even complexity theorists can design algorithms, but that is not primarily what we do. So you go to a person who specializes in designing algorithms, and you tell him, okay, design this algorithm for me, and he'll try to design an algorithm for you. If he could design it, then well and good. But let's say he could not design it. What do you do? If you could not design, if the algorithmist cannot do the job, then you go to a complexity theorist, and the complexity theorist will tell you why that was not possible. So yeah, that was what I told him that time. Okay, so it is not true that complexity theory does not have any practical application. That would be like saying Newton during his time. Okay, he discovered gravity, right? What was the use of gravity during his time? I mean, there would be no use. What was the discovery of Einstein during his time? There would be no use. It is theory that leads to practice, right? And if you see right now, if you see applications like cryptography, the hardness results are what led to cryptography, right? And all the current applications are due to this. If you look at the founding fathers of complexity theorists, okay, they started out with designing algorithms. This communication complexity design started from this VLSI systems and so on, and that is what it is right now. You won't see the application, okay, but many years from now, when this engineering tweaking things from here and there, okay, you tweaking things and taking from the same the water in the well will soon run out. Okay, you need to find a new well. So that is what practice is doing, right? It is taking things from the same well, the water from the same well, and soon the water will run out there. You need a new theory to come up with a new practice, right? So that is what I would answer to you. Yeah.
Yeah, thank you so very much, and such an elaborated and yeah, pretty useful answer. Thank you so
Yeah,
much.
thanks, Gwen. So I'll just take 15 more minutes. Is that fine, Suraj? Gwen?
Yes, yes, perfectly fine.
Yeah, Suraj. Oh, I cannot hear you. Are you trying to unmute? Oh, okay, fine. Right, okay, okay, sure, good. So yeah, I just wanted to quickly revisit, not revisit, sorry, visit for the first time things that are a bit in fashion right now in complexity theory. Okay, so oh, okay, sorry, pseudo randomness. Oh yeah, okay. So see, we talk about so there are okay, we talk randomness, right? So things become easier when you try to randomize. You bring random coins into context, and there are two things. Okay, one thing is you design randomized algorithms. There are really good randomized algorithms which are available right now, right? So and people who specialize in designing randomized algorithms, and they what are they trying to do? They are trying to maximize the probability, and these are again algorithmists at work, right? So design better and better algorithms. And what are the complexity theorists trying to do? They are trying to get rid of randomness. So they are trying to do de-randomization. They are trying to do de-randomization. That is, remove randomness. Remove the. So how do you remove randomness? You cannot directly remove. Okay. So here is an idea. Okay. Come up with bits that appear random. Well, no, but before I come to this, what is randomness? What is randomness really? Well, randomness is when you cannot, you have a string of bits, let's say it keeps coming, you cannot predict what the next bit is. Okay, and it's unpredictable. That is what randomness is. And what happens if your data is not random? Well, they appear very correlated with each other. You want to reduce the correlation, right? And so you want to come up. So what you do is okay, you come up with bits that look random to a very beginner person to a simple algorithm. It looks up random. So let's say I have an algorithm, okay, that requires m random bits, okay, and it has a certain probability. Now it has the algorithm, since it's a randomized algorithm, it has a probability associated. Why probability? If there was no probability associated with it, it would become a deterministic algorithm. It always makes the correct answer, but that is not true. Okay, it takes m random bits, uniformly samples, okay, m length random bits, and probability that the algorithm on the input is some at least two-thirds or something like that. Okay, so this is a BPP algorithm or RP algorithm, whatever. What I want to do is the following. I am trying to fool it. Okay, I come up with m pseudo random bits. The random bits look are actually not random, but because the probability of algorithm is so high, okay, that even if I give it these pseudo random bits, okay, now R is not sampled from this distribution anymore. Okay, what happens is R is sampled from another distribution D, which is pseudo random, okay, which I come up with, and the probability now changes. Okay, the acceptance probability changes by some epsilon. But now what I can do is I can do the error amplification trick, right? So this is what complexity theory is. They asked, okay, and what happened is they asked whether such is it possible to deterministically come up with pseudo random bits. Well, that is a difficult task to do, right? Deterministically come with bits that look random. That is difficult, but what if I give you a very small source of randomness? Let's say I give you very little randomness. So how do I come up with random bits? I actually give you say log m, very small number of purely random bits. Log m number of purely random bits. And I do some processing here, and then I give you m pseudo random bits. That does not affect the probability too much. So this is what pseudo randomness focuses on, and this is what is called a PRG, pseudo random generator. Okay, and this is an entire field. Okay, it again requires an entire course to do this. Okay, and you can check for look up for courses on this, and it's a very interesting field. Okay, you give me very little random bits, and the pseudo random generator will turn it into stretch it. This is actually called a stretch function. Sometimes it is also called a stretch function. It stretches the random bits by a factor of m, okay, by an exponential factor, because it started with log m, and then it gives you bits that are not actually random, but the algorithm already works with a good probability, so it does not affect the fact that it is not actually very random. And now the question is, do such PRGs exist? That is the question, right? Do such PRGs exist? The answer is maybe. Okay. The answer is actually yes, but something. Okay. Now I'll tell you what that but something is. Okay. But before that, I again want to say that there are other interesting things in pseudo randomness also. And there is something called extractors. Okay. There are something called extractors. And I mean, not much is known about extractors, but it is like here what you do is uh, here you are doing the opposite. Okay, you give some m pseudo random bits, and the extractor will come with one random bit. It's doing the opposite of PRG, what PRG does. You come up with many pseudo random bits, and I'll actually compress it into a single random bit, purely random bit or highly random bit. And this is what extractor does. So this is a way to reduce the randomness, right? And this is a method to come up to do de-randomization. Now you might say, okay, fine, if even if such PRG exists, okay, even if such a PRG exists, you are not removing randomness. You still require log m many pure random bits, right? So how are you making it pseudo m random bits? Well, if you can, if even if you know that such a PRG exists, what I'll do is I'll go across all log m length strings. I'll go across all log m length strings, run the PRG on it, and come up with m pseudo random bits. Because I'm going across all, I've sampled the entire distribution, right? I've sampled the entire distribution. If I go across all log m length strings, how much time will I take? M time, polynomial time. In polynomial time, I'll go across all the random bits and I'll obtain the pseudo random bits and then run the algorithm. Well, I've de-randomized. There is no randomness anymore. Get it right? There's no randomness anymore. I'll just go across all these bits and calculate the probability at the end. I'll just keep adding and calculate the probability at the end. So that is the idea, and there is something called Impaglio-Wigderson. Impagliazzo-Wigderson. Remember, it's the same guy who did we do Impagliazzo's theorem? I don't. Okay, Russell Impagliazzo and Avi Wigderson. Last time I think I told you guys that Wigderson won the Turing Award this year, right? So
Yes, yes.
yeah. Impagliazzo-Wigderson, they come up with a pseudo random generator which says BPP equals P if there exists a language in EXP. Actually, it's an E, okay, but I'll just be loose and say EXP, such that L requires circuits of size 2 to the, oh my god, oops, okay, yeah. So if there are very hard there are very hard functions that if there exists very hard functions that require very large circuits, then BPP is equal. That is what it says essentially. And if there exists hard functions, then de-randomization possible, and the other way around. If there exists de-randomization not possible, de-randomization is not possible, then hard functions don't exist. Okay, so this is what is called the hardness versus randomness results, and there is a lot of research going on in this area. There are lots of theorems which are of this flavor, okay, which hints at a connection between randomness and hardness. So now you are taking hardness as a computational resource. You get it, right? Hardness is now a computational resource. Uh, if right, so if you want to make sure that you want to de-randomize something, then you make use of very hard functions. And if you want to and the other way around also. So, but the first direction makes more sense, I think so. But another idea is cryptography. Cryptography relies on existence of very hard functions, right? One-way functions. That is what you say. One-way functions, which are encoding is simple, but decoding is NP hard, right? Do those functions exist? That is the question. Well, those functions exist if uh, de-randomization is possible. If de-randomization is possible, then those functions exist. So here is another application of that. So and this is called hardness versus randomness. Sorry, not hardness versus result. Hardness versus randomness. Okay, and look into pseudo randomness. There are beautiful objects there called, you have extractors and then you have expanders, and pseudo randomness is related to coding theory also, encoding, decoding, and stuff. You can check that out. Okay, next thing I want to tell you about is meta complexity. Okay, so this is complexity of complexity theory. Okay, this is one level above. So meta complexity says uh, things like, uh, okay, if so, uh, we don't know whether P is equal to NP and so on or not. But let's say P is equal to NP, then what would have happened? Let's say P is not equal to NP, then what would have happened? Let's say BPP can be de-randomized. What would have happened? Let's say it cannot be de-randomized. Then what happened? And there is one candidate problem called MCSP, which is uh, being tried to which is the candidate problem for meta complexity, which is minimum circuit size problem. It says uh, uh, given a particular truth table, okay, what is the smallest circuit that computes it? Now you can already see that this is a meta complexity flavor. Okay, proving circuit lower bounds is already difficult for us to do. Now what you are trying to come up with an algorithm which actually does this. Okay, now that is what meta complexity is all about. And so you also have this impagliazzo again. Okay, Russell impagliazzo, 5 volts. I think there was a recent sixth edition also. What it says is what is the world we live in right now? Right now, okay, is it what is called algorithmica? Algorithmica is P equals NP, or is it? I forgot all the names. There is something called heuristica, um, minicrypt, cryptomania. You can look it up. Okay, and there is one more here, which is when P is not equal to NP. Let me see. Q 5 volts of impact liazzo. Algorithm की Eureka Pesiland, yes, Pesiland. Pesiland is when P is not equal to NP. Okay, and heuristica is NP is hard on average or easy on average. Okay, minicrypt is cryptomania is one-way functions exist. Okay, and so you can decrypt it and so on. You have cryptography based things. Okay, there. But yeah, meta complexity is one interesting field which is very much okay. Every year in a conference you have these meta complexity papers. Okay, and okay, that is the second thing. And next thing that is gaining popularity is KRW conjecture. Okay, since a long time it's gaining popularity. Again, Karchmer, Raz, Wigderson. I vote for heuristica. Everything is so very uncertain and hit and try. Yeah, yeah. So yeah, the papers, the papers get published in meta complexity are okay. So here is the evidence. So we prove the following hardness results, and so here is the evidence that algorithmica does not exist. Here is the evidence that this does not exist. So that is a nice thing. Yeah. Right. Good. So KRW conjecture. Okay. What did KRW conjecture? So the question is as follows. Okay. So you have two functions f and g. Okay. And you have a hardness measure. Okay. You have a hardness measure of f and a hardness measure of g. Okay. Now question is you are computing f o g. What is the hardness of g? How hard is it to compute the composition of functions? That is the question. So what Karchmer, Raz, Wigderson say is that the hardness of f compose g is at least as hard as computing f separately and computing g separately. Correct? So you compute f separately and you compute g separately. Okay. Oh, add. Sorry, not compose. Add. So these are also what are called direct product theorems. Okay. But the original is in terms of communication complexity. The communication complexity of computing the composition is the sum of the communication complexity of this, at least. So this is a conjecture, and intuitively also it makes sense. When you take two difficult functions, suddenly you compose them, you cannot create something which is easier. So it has a deep philosophical impact also, and this is what they are trying to prove. Okay, and there are monotone versions. Okay, and because of that Kashmir-Wigderson theorem, you can even write it in terms of depth of circuits. You can prove it either way. So yeah, and then there are lots of papers on this. So there is good amount of research going on here. Okay, trying to prove the Kashmir KRW conjecture, and finally you have range avoidance problem. Okay, and I'll close off with that. Range avoidance. Okay, it's also closely related to meta complexity. That is, you are given a multi-output circuit. Okay, multi-output circuit. There is an input. Okay, you have input bits, and the multi-output circuit is such that the number of outputs is strictly less than the number of inputs. By the pigeonhole principle now, or sort of the anti-pigeonhole principle, you always have an output that will never come here because the number of inputs are more. Okay, and this is sort of a 1-1 mapping, right? So give me that output. Give me the output y such that for any input I give, the evaluation will never give me y. So if I have the input set of inputs and I have phi and it maps to a set of outputs, give me something that is outside the range, something that avoids the range. That's why it is called range avoidance problem. Now this is a notorious problem. Okay, it is the only thing that is known about it is an FP to the NP. Oh, it's not even in FP to the NP. I think it's in ZPP to the FZPP to the NP or something like that. It is a difficult problem, okay, trivially. And interesting thing is people have discovered that even if you prove it for a small circuit, even if you prove it for a constant depth circuit where each fan-in is, constant, some K, okay, um, you can solve the entire range of it for any circuit. So these kind of interesting things are there. And why is it interesting? Because if you actually prove that it can be done in polynomial time, range avoidance, or even in FP to the NP time, you can actually prove that you can actually construct PRGs, extractors, expanders, and all these interesting pseudo random objects very easily. So range avoidance is a very interesting area right now. Something I've not mentioned here is what is called arithmetic circuits, but that will require a long session. I would recommend you check it out yourself. Okay, so this is also an area where there has been a steady amount of research here. So I recommend you to look into these. Okay, Google them, check them out once, check out for talks in YouTube. Okay, and you can even mail me. Okay, and ask me for resources. Then maybe I'll be able to guide you, or maybe even if I don't know, then I would love to explore these areas. So yeah, any more questions? Final closing questions. Okay.
No, so yeah, the entire, I mean, this session was pretty good. And so, yeah, so whenever you take TA-ship for another subject in the next semester, then let me know. Yeah.
Oh, right.
Or-
Thank you. Well, yeah, I okay. Let's see. It may be even something like discrete math. So maybe I don't think you would want to credit that. So it may not be something very advanced, but even if you are interested, I'll still let you know.
Yeah,
So
sure.
yeah, I'll let you know. I think I have your email. Yeah, right. Uh, Great then. Uh, okay. Then I think we can close it off. So I think um, the exams are on 27th, right? Suraj is giving the exam. You were telling me. So you are also giving the exam.
No, I'm not appearing in the examination.
Oh, okay. Great. Okay. Wait, I'll just